What's up, students? Mr. Harrison here from school. Here is your video covering the slideshow on waves and sound. So first thing, before we get into anything about sound itself, we're going to just have to talk about the properties of a wave. The definition of a wave is that it's a repeating disturbance or movement that transfers energy through matter or space. It's very general. This unit on sound waves is going to talk about just mechanical waves. So those are the types of waves that can't transfer energy through space. They must only transfer it through matter. The first thing I wanted to talk about is the fact that a wave, if it's a mechanical wave like a sound wave, since it can only transfer energy through matter, it doesn't actually do a whole lot of displacement of the matter. So think about when you have a floaty in the water, in a pool, in a lake, whatever, and you throw a rock into the water. After 10 waves pass by, that floaty is not going to be where the wave is. The wave is going to pass through the area by the floaty. It'll displace it a little bit, but really the waves are transferring the energy, not the actual material. So there's material through which the wave travels, but that material doesn't get transported. Just the wave energy gets transported through the material. So the water itself, or the flotation device, or whatever it is that's in the water, doesn't get moved, doesn't stick to the wave. The wave passes through where that object is, and that's an illustration of the fact that the waves don't actually transport the material; they just move through the material. All right, so as we said, waves are rhythmic disturbances. Rhythmic as in repeated, think like a metronome or like a drum loop. They're repeated, and they carry energy through matter or through space. But in this unit, we're sticking on the waves that just transfer through matter. But that rhythmic implies that it's repeating. The next term is medium, and a medium is whatever the material is that the wave is transferring energy through. It could be a solid, it could be a liquid, it could be a gas, it could be a combination of a solid and a liquid, or a solid and a gas, or a liquid and a gas. It could be any combination of the main phases of matter. Then you have a second kind, which we'll talk about in the next unit, and that's electromagnetic waves, and those are special because they don't need a medium to travel. Mechanical waves, like sound waves, need a medium to travel through. So here's some of the properties of a wave. Amplitude starts with the same letters as the word amp, or amplifier. An amplifier is going to turn up the volume, right? It's going to give it more energy. So amplitude is essentially the energy carried by the wave. In a transverse wave, it's the distance from rest to crest. That'll make more sense later. And that's perpendicular to the wave's direction. In a compressional wave, it depends on how tightly the medium is compressed, or the density of the medium at compression. All that'll make sense in a little bit. That's just a little bit of kind of like the definitions for you. Transverse has a specific measurement for amplitude, and so does compressional wave. Then you have wavelength, which is signified by a Greek letter called lambda. That's what that is. Kind of looks like a wave if you think about it. Transverse wavelength is the distance from crest to crest. It could also be the distance from rest to rest. In a compressional wave, it's the distance from compression to compression. Either way, whether it's a transverse wave or a compressional wave, and again, we'll talk about what both of those look like in a minute, but either way, it's the distance between two corresponding spots on a wave. Or putting it more simply, it's the distance between any point on a wave and the point where that specific part of the wave gets repeated. So like if it's the crest, that's like the mountaintop, it has to go till the next mountaintop. Oops. Then you've got frequency, and that's how many times the wave repeats per second, or how many wavelengths you have per second. So if you can almost picture it as how squished together the wave is. And then period is the time it takes for one wavelength to pass a point. Here's your two types of waves we mentioned. You've got compressional, or that's also called longitudinal, and then you've got transverse. As you can see with the compressional, the wave travels the same, the compressions or the energy in the wave travel the same direction that the wave travels. So it's like a straight line. In a transverse wave, the energy is traveling up and down, but the wave is traveling left to right. Whereas a compressional wave, the energy is traveling left to right as the wave is traveling left to right. So it looks a lot flatter, whereas a transverse, you've got energy going in perpendicular directions, up and down, as the wave travels in the perpendicular direction to that, which is left to right. So you can kind of get a visual of what transverse looks like as compared to compressional / longitudinal waves. So energy transport for both of them is going left to right. But in a compressional wave, energy itself is going left to right, whereas in transverse wave, the energy is moving up and down. So transverse wave, we have that word perpendicular to the direction of the wave motion. Wave's going left to right, energy is going up and down, perpendicular to that left-right direction. And in a transverse wave, you've got some guts to it. This flat line here would describe a scenario called rest, and that's what the wave would look like if it had no energy. The mountaintops here are called crests. There's one here, there's one here. The bottom part, you can't really see it, it's called rests. So rest, the valley. Sorry, not rest, excuse me. This is rest. This is called a trough. My apologies. I'll say that again. The mountaintop is called a crest. The valley here is called a trough. And the way that I remember that, even when I forget it sometimes, is that I know that when you feed a pig, the thing that the pig eats out of is called a trough, and it's down by the ground. So crests are like mountain crests, mountaintops. The trough is where the pig eats out of, and it's down on the ground. So crests are on top here, troughs are on the bottom. Again, this line where it's right in the middle is called rest. And as you can see, there's two measurements for amplitude. The measurement from the rest area to the top of the crest, or from the rest area down to the bottom of the trough. So it's basically the distance from the rest to the farthest point from the rest. And then you have one last measurement, which is from one mountaintop crest to the next mountaintop crest, or it could be from one valley trough to the next valley trough. It's going to be the same distance, and it's called wavelength. It's the measurement between any point in the wave and the point where it repeats itself. So if you're going up, here's the top of the crest. Here it goes down into the trough, all the way back up past the rest to the next crest. Right here, this horizontal measurement is wavelength, whereas amplitude here is a vertical measurement from rest to the top of the crest. Another interesting thing is that the amplitude corresponds to the amount of energy that the wave carries. So if you're asked, how do we tell how much energy the wave has? Well, measure the amplitude, and it's the same. That's your answer. All right, so in the longitudinal wave, aka compressional, the media moves in the same direction of wave motion. Another way to put it is it moves in a direction parallel to wave motion, same parallel. Whereas in the transverse wave, it moves in perpendicular directions, or opposite the direction the wave travels. All right, so here's a compressional wave. And by the way, this is what a sound wave is. It looks like this. Sound waves do not look like this. That's a transverse wave. Sound waves look like longitudinal compressional waves. There's two main parts of a compressional wave. You've got the part where it's squished or compressed together. That's called a compression. Makes sense, right? Compressed areas are the compression. And then you've got this area where it's stretched apart. That's called rarefaction. There's going to be another word later called refraction. Sounds kind of like it, but it's a totally different thing. The stretched out part of a wave, sound wave or a compressional longitudinal wave, is called rarefaction. Rarefaction. Like it's rare and it's a faction. Not a fraction, a faction. Rarefaction. Then the squished together part that's compressed is called a compression. Now, if you take a measurement from any point in the wave to the point where it repeats itself, you're going to have wavelength. So this one starts right before the compression. If you follow it along until right before the next compression, that's going to be right here. So this whole distance is wavelength. This one starts right at the start of the rarefaction. You follow it over to the start of the next rarefaction, and that's right here. It's going to be the same distance, and you can measure it anywhere as long as you find the point where it repeats itself. And in the compressional longitudinal wave, the amount of compression, or how much matter gets squished together, equals the amplitude. And we'll kind of demonstrate that with the slinky in a little bit. All right, last thing here. Frequency is the number of waves passing a point in a second. So look at these two waves. Which wave has disturbances? These crests and troughs are the disturbances. Which wave has disturbances more frequently? Is it the top wave or the bottom wave? If you look at it, this one has 1, 2 crests. This one has 1, 2, 3 crests in roughly the same distance. So the second one has a higher frequency. And as you can see, it means it's just kind of squished closer together. It's measured in a unit called hertz. You may have heard that before. And the interesting thing here is there's a relationship between wavelength and frequency. If the wavelength gets shorter, that means it gets kind of squished together, the frequency increases. And the energy also increases because it takes more energy to do more of these disturbances. So the frequency and the wavelength have what's called an inversely proportional relationship. When one goes up, the other goes down. So when wavelength decreases, shorter wavelength, frequency increases, higher frequency. But when wavelength increases, longer wavelength, frequency decreases, it would have a lower frequency. And energy and frequency go together. Where frequency increases, energy increases, and where frequency decreases, energy also decreases. So go ahead and close this down and start answering the questions that go with it.